Hello everyone. So let's first talk about discuss the final exam schedule. So I sent the email this morning. I put the exam on based on the schedule. I put it on May the 4th, starting from 1 to 3. But for some of you, if you have other exams starting in the morning and ends in the noon, so we may consider, one option is that we may consider reschedule this to be later in the afternoon. So let's say if we start at, we can start at either 2 or 3 p.m. So it's 2 to 4 or 3 to 5 p.m. on May the 4th. Will this work for everybody here? Okay, any of two slots, either work for me. Okay. Then I will resend another email. Okay. So I will resend another email. We will try 2 to 4 first. Let's make it 2 to 4. 3 to 5, okay. So it looks like this is the only option, but let's try this. Let's try this. Okay, so let's try to make it 3 to 5. The last homework going to post it. Did I? Oh yes, I forgot to publish this. Sorry about that. Let me see this. Today is. I think homework 10 is actually. Wait a minute. It's 2021, so homework 9. Just. I'm not sure how many of you have finished homework 9, so but let me just publish it, and let's say homework 9, let's make it yeah, so this homework 9, I can finish lecture 9 today, so next Tuesday homework 9, homework 10. Okay, I will set up, let me set up a due date. I know it's okay. This is, if homework 9 is due at 26th, the semester ends on 27th. Then I will make homework 10 optional. Okay, let's make it optional. But however, note that the final exam do include homework 10, lecture 10 materials for lecture 10. So optional for extra credit, that is no, I think to make things simpler, otherwise I will have to recalibrate everything. How about we just remove homework 10? We just remove that, but I'm gonna post homework 10 and solution online. So, and it will be included in the final exam. So the due date, add it. Oh, so I can just unpublish that. So let's just count up to homework 9. Homework 10 is removed. So everything can be, so I don't have to recalibrate everything. And I will post the solution of homework 10. So you can take it, you can follow the solution, follow the homework examples, and still go over the, also go over the review lectures. Not replace lowest score. I mean, in the end, I may do a curving in anyway. So I just want to make it simpler for me to calculate final grade. So I will just, the evaluation will just cover the first 9 homeworks. Yes, I will post it right now.
Just to verify with you, the final exam is on May 4th, not the 3rd, correct?
So can you say that again?
Yeah, just to double check, the final exam is scheduled for May 4th, not the 3rd, right?
Yes, May 4th.
Okay.
May 4th, 3 to 5. 3 to 5. Okay, I will do that later. I will send the email right after the lecture. And I have put it here, May 4th, 3 to 5. And these are some 6 plus 1. So we have 2 hours, 2 hours, 6 problems plus 1 bonus. So it covers, most of them covers the last 2 lectures. So it is not accumulative. But some of them, like the bonus, may depend on Fourier transform or the sampling theorem or some, like all the previous materials. Okay, so we can communicate over the email. So last time we discussed about the stability and the causality of LTI systems by looking at the Laplace transform. Now the key message is that in order for a rational LTI system, here rational means the Laplace transform takes a rational form. In order for a rational LTI system to be causal and stable, we must satisfy that all the poles of this of the rational Laplace transform must be in the left half plane of the complex plane. So they are real parts. All the poles must be to the left of the y-axis. And this example shows that in order for a system, LTI system has different properties, the corresponding system impulse response can be substantially different. So if we consider an impulse response whose Laplace transform takes this rational form, so this is a rational Laplace transform, and we do a partial fraction expansion, we can have these two smaller fraction numbers. And then we have, and then the key here is to consider its region of convergence, which depends on how the system behaves. So here we discuss 3 cases. In the first case, if we want the system to be causal, if we want such an LTI system to be causal, then based on the causality criterion, causal and rational LTI system, in order to be causal, we need to satisfy that the region of convergence is to the right of the rightmost pole. And considering this example, we have 2 poles. One is -1, one is 2. So clearly 2, the pole 2 is the rightmost pole. So based on this criterion, we can derive that the region of convergence must be to the right of the rightmost pole. So it's the real part of S bigger than 2. So this is ROC. Okay, so this is the ROC in order for the system to be causal. Okay. And once we have this ROC, then we can go back and find out the inverse of this Laplace transform. Okay, so this reduces to the examples that we have discussed previously. So given such a Laplace transform, given this ROC, look into the table and we can find out the inverse, which takes this form. And you can see that it is indeed a causal signal, the causal impulse response because of this UT. However, this system is not stable because according to the stability criterion, the ROC must include the y-axis. But in this case, the rightmost pole 2 is to the right of the y-axis. So this region of convergence does not contain the y-axis. So therefore, if for this example, if we want the system to be causal, then it is not a stable system. Now, on the other hand, if we want the system to be stable, which means the ROC must contain the y-axis. But now looking at this Laplace transform, we have these two poles. One is -1, one is 2. So here's 0. Here's the y-axis. So we know that for such a rational Laplace transform, the ROC, according to the basic properties of region of convergence, the ROC can only have 3 possibilities. One is to the left of -1. One is between -1 and 2, this vertical strip. And the third case is to the right of 2, right? Because the ROC must be parallel to the y-axis and must not contain any pole. So these are the only 3 possible region of convergences. And then among these 3 possibilities, we need to find out which one of them can include the y-axis. And clearly from this example, because the 2 poles are located to the left and to the right of this y-axis, so the only possibility is that the ROC is between -1 and 2. Therefore, in order for the system to be stable, the ROC should be between -1 and 2. Okay, and then you have the region of convergence, you have the Laplace transform, you can find out the inverse. So because we have this part of ROC, so this is to the left of the pole 2. So which means with this ROC, for this part, the corresponding ROC is this one. And then if you look into the table, now such a Laplace transform will lead to a left-sided signal, So ROC is left-sided. And for the other fraction number, for this part of the Laplace transform, the pole is -1, and correspondingly, the region of convergence is this part. So it's bigger than -1, it's to the right of -1. And then if you refer to the table, this will give us a right-sided signal, So this is the case for a stable system. So now we have discussed these 2 cases of the ROCs. One is to the right of 2, one is between -1 and 2. And the last case is to the left of -1. So if for this system the corresponding ROC is to the left of -1, then we can see that it is neither a causal nor a stable system, because it violates both criteria. And correspondingly, if you can find out the system impulse response. With this ROC, the inverse of this Laplace transform becomes this one. So this is clearly is not causal because of U negative t, and it is not stable because this part blows up to infinity. Right? Once if t goes to negative infinity, this e to the e to the power of negative t blows up to infinity. Which makes the signal unstable, which makes the impulse response not absolutely integratable, and therefore the system is unstable. So again, from this example, we can see that for different types of systems, the corresponding ROC will be completely different. And you will see this type of problems in the homeworks and the exams. Like if I give you a particular specific Laplace transform, and suppose this is the Laplace transform of impulse response of an LTS system, then you should be able to discuss, find out the corresponding impulse response associated with different types of systems. If the system is causal, how do you find out the corresponding impulse response? The key is to first figure out the corresponding region of convergence. And then based on that, you can figure out the inverse. And in the Fourier transform lecture, we have seen this type of LTS systems characterized by partial differential equations. So here we can apply the Laplace transform to analyze these systems. So for example, this is a generic linear constant coefficient differential equation. Okay. It's just in a very general form. And then we can take the idea is to take a Laplace transform on both sides, and then by leveraging the differentiation property of Laplace transform. So these higher order derivatives after taking Laplace transform becomes s to the power of k, well, k is the order of the derivative and times ys. And on the right hand side, you have the same thing times xs. And then the system response is basically h equals to capital Y over capital X. So you rearrange this equation so you can figure out the system response h to be this summation over the summation on the left hand side. Okay. So this is exactly the same as what we have done in the lecture 6 in the Fourier transform lecture. And then after that, we obtained the Laplace transform of this system. Again, we need to talk about the ROC, right? When we talk about Laplace transform, ROC is always the most important thing. So how do we figure out the corresponding region of convergence? The region of convergence can be determined based on the properties of the system. Right? So you need to look into the context of the problem. If we are talking about the causal and stable system, then those conditions will impose some conditions on the ROC. And from there, you can figure out the region of convergence. Now here's a concrete example. It's a RLC circuit. And for such a standard RLC circuit, the system equation is described by this partial differential equation. Well, I believe Y is the voltage. Oh no, Y is the current, and X is the voltage. But for such a partial differential equation, we take Laplace transform on both sides and rearrange the equation a little bit. So this second order differentiation becomes s to the power of 2 times ys. And here's a first order differentiation which becomes s times ys. And this is just the zeroth order, simply ys. And xt becomes xs. So in the end, you can find out h, which is y over x, equals to this, takes this form. So this is a rational form. So this is a LTI system with a rational Laplace transform. And then you can talk about under what conditions will this system become stable or causal? That will depend on the region of convergence of this Laplace transform. And this is I think we have mentioned this in the previous lectures. So these are block diagram representations of a system. I think we can quickly go over this. So basically, if you have this is like a parallel system where you have H1 and H2, they are added up and become HT. So the diagram may look like so the system diagram may look like this. So it's a parallel system. But in general, based on this equation, you can take Laplace transform and obtain this system equation in the S domain, okay, instead of the time domain. And this is a serial system. Well, it's basically a convolution of two signals, and then you take Laplace transform, they become product in the S domain. And this is a feedback system because on the left-hand side, you have the output of the entire system. But on the right-hand side, the output is further involved in the back into the system. So you can see here we have YT involved on the right-hand side. So which means the output is feedback to the system. And by directly taking Laplace transform on both sides, we obtain this equation where all the convolution becomes product. Okay. And then we have y on both sides. So rearrange the equation and we can derive that y over x equals to this one. Therefore, if we view H1 and H2, so H1t and H2t can be viewed as the impulse response of two separate LTI systems. And then their corresponding Laplace transform or system Laplace transform is capital H1, capital H2. And then this entire feedback system is built upon these two smaller LTI systems and also involves feedback. So for this entire system, the corresponding frequency response is characterized in this way. It depends on the response of both H1 and H2, these smaller systems. So usually once we are given this equation, we can directly take Laplace transform and then derive the system equation, derive the frequency response. So these are, here are some more concrete examples. Well, this is a system described by a partial differential equation. So you follow the standard steps, take Laplace transform, and then you can derive that the system response, capital H, is given by this 1 over S plus 3. And this can be viewed as a feedback system. In the following sense. So this looks like, because it's a fraction number, so it falls into this general form. And what we can do is to rewrite it into this form. So we divide by S on both sides, on the numerator and denominator. So this is an equivalent transformation. And then we can view this. Now we can compare this one with this feedback system. So this would be our H1S, right? And it's 1 plus. Here we can view this as 1 over S times 3. Right, so this is our H1S defined here, and this 3 is H2S. Right. Therefore, you can understand this system as a feedback system using this template. This is a kind of a template of feedback system. And we know that this system, H1S equals to 1 over S, for this specific Laplace transform, it corresponds to an integrated system. You can find this in the previous slides of this lecture. So this corresponds to an integrated system. And the second one, it has a constant Laplace transform. Okay, so this is a feedback system. And the other example is we are given such a Laplace system with such a Laplace transform, and we can write it in this way. So we can view this as a product of two systems. So it falls into this template. Well, we can define this, we can view this as H1 and this as H2. Okay, so H1 is 1 over S plus 3. This is the feedback system that we mentioned in this example. So the first system is this feedback system. And second system is H2S equals to S plus 2. So this corresponds to a differentiating system. And this constant 2 means scaling in the time domain. So it's a shift in the frequency domain, which corresponds to frequency modulation in the time domain. Okay, so you can find out, you can refer to the previous slides for the differentiated system. So this shows that for these rational Laplace transforms, okay, we can always decompose them or analyze them, or view them as a composition of multiple subsystems. Okay, and these are the basic templates that we can use to understand to decompose the big system into smaller subsystems. And we have seen this type of rational Laplace transform many times, right? The numerator is a polynomial and the denominator is something like 1 plus or a constant plus another product of polynomials. So this usually means the system has a feedback, and the system can be decomposed into 2 or more smaller subsystems. Okay, so these are the basic Laplace transform. So the key message when you review this lecture up to the slide 31, right, the most important part of Laplace transform is the region of convergence, where everything is around ROC. So next we will introduce another very useful Laplace transform, a variant of Laplace transform called unilateral Laplace transform. And you may have seen this in other courses like circuit courses or the other control related courses. So the difference, the previous Laplace transform, which is the standard Laplace transform that we introduced at the beginning of this lecture, we call it the bilateral Laplace transform. Now, what is the difference between bilateral and the unilateral? The only difference is that bilateral means in this Laplace transform definition, we take integration starting from negative infinity to positive infinity, right? Same as the Fourier transform. The transformation, the integration ranges over the entire time domain. But here, so that's why we call it bilateral, right? From negative infinity to positive infinity. So it's bidirectional. But here we define another type of Laplace transform called the unilateral Laplace transform. The only difference is that we start from 0 negative instead of negative infinity. This is because later we will see there are multiple reasons, multiple motivations for introducing this Laplace transform. One is that later we will see that this type of Laplace transform is sensitive to the initial conditions. So we can use this type of Laplace transform to solve partial differential equations that with some given initial boundary conditions. This is one. The other motivation is that because the integration starts from 0 negative, so intuitively this integration only depends on the signal while t is greater than or equal to 0. Okay, only depends on the positive part of the signal in the positive time domain. So we know that a signal in a positive time domain is called a causal signal. Right? That's the definition of causal signal. So by this property, such a unilateral Laplace transform will be particularly useful in analyzing causal systems. Because for causal systems, that HT only takes values in the positive time domain. And in that sense, we just need to consider the unilateral Laplace transform instead of the bilateral Laplace transform. Okay, so this is the definition of a unilateral Laplace transform. The only difference is this: the lower limit starts from 0 negative. And for such a unilateral transform, the region of convergence is always a right half plane. Why? Because you can view this integration intuitively, you can view this integration as you can extend it to the bilateral transform by introducing a UT. Again, we are playing this trick. You can introduce a UT. This UT will make the lower limit to start from 0. Therefore, it is essentially, you can intuitively view this as a normal, a standard Laplace transform applied to such a signal. And we know it's xt times ut, no matter what xt is, xt times ut is always a right-sided signal. It's a causal right-sided signal. So by the properties of Laplace transform, the ROC of this signal is right-sided. Therefore, the conclusion is that considering this unilateral transform, the region of convergence is always a right-sided plane. So there's a common zero negatives talking about the initial conditions, such as charge in capacitor before switch. I think yes, we will see in a few slides. We will see many examples, circuit examples, where we are given the initial conditions. Sometimes we are given initial conditions about voltage. Sometimes it's about the initial conditions of current. Yeah. So this will make this transform depending on the initial conditions. We will see from the basic properties of this unilateral transform. So this is the first property of unilateral Laplace transform. We always have right-sided ROC, okay, because we're considering we're kind of truncating the signal into a right-sided signal, and then performing a standard Laplace transform. And then another property, another property is that for causal signals, the unilateral and the bilateral Laplace transform are the same, because we know causal signals. For causal signals, xt equals to xt times ut. Right? That's the definition of causality. So in that case, these two transforms are the same because the signal only occurs after 0. So you can just consider this integration starting from 0. And here's an example. Find the unilateral Laplace transform for this signal. This part is a standard exponential signal, right? E to the power negative at times ut. And then we have this coefficient, t to the power of n minus 1, and this is a factor of n minus 1. So first of all, because xt, because of this ut, we know xt is causal. Okay, it's a causal signal, and due to this causality, we know that unilateral and bilateral transforms, they are identical for this signal. So here are the steps that we can follow to find out the unilateral transform. So first of all, we are familiar. So this signal is familiar to us. We know is Laplace transform, standard Laplace transform. Okay. So we can start from this signal and then consider introducing this coefficient by leveraging the properties of Laplace transform. So because this signal is causal signal, therefore the unilateral transform and bilateral transform are the same. So from the table that we discussed at the very beginning of this lecture, we know that this signal has such a Laplace transform with such a ROC. Right? This is a conclusion. And then because it is causal signal, we know that the unilateral transform is identical to the Laplace transform. So the first observation is that the unilateral transform, well, it is denoted by UL, unilateral Laplace transform. The UL is essentially the L of this signal. Okay. And from the previous discussion, we know the Laplace transform of this signal equals to this one, and the region of convergence equals to is to the right of negative A. Okay, so this is the first step. By leveraging the property of a signal, we can identify the unilateral transform. And then the second one is to introduce this coefficient. Now here I will just follow this hint. The observation is that this coefficient can be introduced by leveraging the differentiation in the frequency domain property. We can apply this property multiple times. So essentially, by the differentiation, property in the S domain, such a signal corresponds to such a Laplace transform. Okay. So in the time domain, we add t to the power of n minus 1. We add this coefficient. We add this scaling factor. And then in the S domain, this will lead to -1 to the power of n minus 1, and then a differentiation of the original Laplace transform by n minus 1 times. And such a differentiation will give us this factor, because you are taking this, you are taking derivative n minus 1 times. So each time you will have a factor coming out. So putting them together, in the end, we will have this overall factor. And combining both parts, we can conclude that the unilateral Laplace transform equals to this one. Okay, you still need to move this factor to the left-hand side so that you can have this signal. But once you do that, the unilateral Laplace transform reduces to this one with the ROC given by to the right of negative A. So to summarize, the trick is that first of all, we observe the signal is a causal signal. So the unilateral and the bilateral Laplace transform are identical. So in the end, we just need to figure out the normal Laplace transform. And then we start with the basic signal. For this one, we know the normal Laplace transform corresponds to this. And then to introduce this additional factor, we apply the differentiation property in the frequency domain multiple times. And then we can figure out the Laplace transform of this signal takes such a form. And then by combining this with the first observation, so the Laplace transform is exactly the unilateral Laplace transform. Okay, so this is a very useful trick that we will leverage frequently. So whenever the signal is a causal, okay, unilateral is always the bilateral. So we can start with the normal bilateral Laplace transform. And here's another example, find unilateral transform for such a signal. Well, in this case, it is no longer causal, but it is close to causal in the sense that we can view it as a starting from the causal signal and shifted by 1 to the left by time shifting. So for this signal, first we observe that because of ut plus 1, because of this unit step function, the signal will be non-zero whenever t is greater than -1, but because the ut is shifted to the left by 1 unit. So this signal is non-zero for t greater than -1. And the key observation here is that looking at this part, so let me write it here. Right. So this is the part that involves time t, right? E to the power of -at times ut plus 1. And this signal, it starts from -1. And the key observation is that the unilateral, if we consider the unilateral Laplace transform of this signal, it equals to unilateral Laplace transform of ut. So why is that? You think about it. So we can reduce ut plus 1 to ut. It's not causal. The signal, this signal is not causal because of ut plus 1, right? It starts from -1. The signal starts from -1. Causal, we need to start, in order to be causal, we need to start from 0. So this is not a causal signal. So the key observation is that the unilateral, because this is a constant coefficient, right? So we can put it aside. Now consider this part. This is the real signal part. This part depends on t, signal, the time index t. Now for such a signal, its unilateral transform can be actually reduced to the ut plus 1. We can replace it by ut, because again, we are leveraging the property of the basic definition of unilateral transform, because unilateral transform always starts from 0. So you write out the definition of unilateral transform of this signal. Right. So this is the signal, and this is the unilateral transform. Now, because it starts from 0, but here we have ut plus 1, and these two, they have a conflict. So in the end, we just need to consider, now ut plus 1 means that the signal starts from -1. However, the integration starts from 0. So in the end, we just need to consider the signal starting from 0. Okay. Because there's a constraint on the lower limit of this integration. Because of that, we can always restrict this to be UT. Right, so this is a special property of unilateral transform. Okay. So this one, the unilateral transform of this signal reduces to the unilateral transform of this signal. And now it is a causal signal. Now it is causal, right? Because of UT. Therefore, okay, so let's keep going. Now starting from here, the unilateral transform of this causal signal, because it's a causal signal, so the unilateral transform equals to the normal Laplace transform. And we know from the table that the Laplace transform of this signal is given by 1 over s plus a, and with a region of convergence. Okay. Now, connecting this with this equation, in the end, we conclude that the unilateral Laplace transform of this signal is given by this one. And then the original signal is basically a scaled version of this signal, right? It's a constant e to the power of negative a multiplied by this signal. So by taking unilateral transform, we will see unilateral transform is also linear. So in the end, we conclude that the unilateral transform of xt is just this one multiplied by this constant coefficient. Right, so this is how we derive or compute the unilateral transform. We always think about how to leverage how to transform the signal or modify the signal in a way such that we can connect the unilateral transform to the normal Laplace transform. Because all the tables, all the pairs of Laplace transform that we have discussed, they are normal Laplace transforms. So we always connect, like in this example, we connect unilateral transform of this signal to the unilateral transform of this causal signal. Because by leveraging the property of unilateral transform. And then because this is causal, right? Causality is very important. Now, because the signal is causal here, so the unilateral transform equals to its corresponding Laplace transform. And we know for this one, we know the Laplace transform. So in the end, this is how you figure out the unilateral transform, by connecting it to a Laplace transform of a causal signal. So we will see this, we will play with this trick numerous times. Okay, now example 3. Find the unilateral. By the way, we use this notation to denote the unilateral transform. Right? So this is bilateral, and this is unilateral. What are the restrictions to using this? I think here we are, if you look at each step, we're trying to leverage all the basic properties of a unilateral Laplace transform. So the idea is to reduce the unilateral Laplace. Okay, so the first of all, for this one, when you start with this example, when you start with this signal, the first challenge that you can see is that the signal is not causal, right? If the signal is causal, then we know that the unilateral, bilateral, they are the same. So we can just compute the normal Laplace transform, and then that's it. So the challenge here is that the signal is not causal. So the key step here is to find out, to observe that the unilateral transform of such a non-causal signal can be connected to the unilateral transform of a causal signal. Connect to a unilateral transform of causal. So causality is the key to the unilateral transform. Once we connect it to the unilateral transform of this causal signal, then the rest of the step is very simple. Because it's causal, we know the unilateral transform equals to the normal Laplace transform. And here, the normal Laplace transform is already discussed in the previous slides. So we can have that from the table. So in the end, this is how we solve the unilateral transform of a non-causal signal. Okay. Reduces to a causal signal first, and then from there, the unilateral transform can reduce to the normal Laplace transform. Yes, you can do this. You can do this without any risk. So basically, okay, what you can do is this. For any signal, okay, it can be causal, non-causal, whatever, any signal. The unilateral transform equals to the unilateral transform of xt ut. Right? Because why? Because the unilateral transform in the definition, the integration starts from 0. So I can add a ut for free. So ut also restricts the signal to start from 0. So there's no loss of generality here. So, and then connecting this to this example, so the unilateral transform of e negative a t plus 1 ut plus 1. Okay, I view this as a signal. It equals to unilateral transform of ut plus 1. I can add a ut for free, right? By this property, I can add a ut for free. And these two, you can quickly check it is basically ut. It is basically ut. And then by the linearity, now again, so this is another way to write out the previous proof. And by the linearity, I can pull out a constant factor. And inside, I would have this. I pull out this constant factor. Inside, I have this normal causal signal. And because it's causal, it equals the Laplace transform. Now we know the Laplace transform of this causal signal. So I don't have negative sign here. Right. So this is how we always reduce the non-causal signal to a causal signal by leveraging the properties of unilateral transform. We will see this later in the other examples. So this is find a unilateral transform for this modulated signal. Again, you can see that xt is cosine times ut, so it's a causal signal. Okay, but once you have that, it's very simple. Because of that, the unilateral transform is the same as the bilateral, the normal Laplace transform. Okay, so you just need to figure out the normal Laplace transform of this signal. And this is the product of two signals. So we can, so we can view this as a modulation. So it's a UT signal modulated by cosine. And then we can try to use the frequency shifting property whenever we see such a modulation multiplied by cosine. So the idea is that, first of all, for UT, we know that the Laplace transform is given by 1 over S with the ROC to the right of 0. And this is, we have discussed this example in the previous slides. So starting from there, we apply the frequency shifting property to address the cosine. Okay, so it's standard. You decompose it using Euler's formula and then apply the frequency shifting property. So in the end, this is the Laplace transform that you obtain. Okay, you have, because of this modulation, you have two copies. One is shifted to the left, one is shifted to the right. So this is the Laplace transform you obtained with this ROC. And then because the signal is causal, so you can conclude that this is indeed the unilateral transform. Okay, so this example is quite straightforward. Okay. And example 4 is a very interesting application that shows the power of unilateral transform, unilateral Laplace transform. The problem, the question here is that find given unilateral Laplace transform in a rational form, in such a rational form. And remember, here we're talking about unilateral transform, not Laplace transform. So given the unilateral Laplace transform in this form, find out the inverse xt. Now you may wonder, here we don't have region of convergence, right? If we want to solve the inverse in the previous normal Laplace transform, we always need to identify the region of convergence. And here, this is really the power of unilateral transform. Once we are given the unilateral transform, we don't have to, the region of convergence is implicitly given. So you don't have to know the ROC explicitly. Okay, so let's figure out, let's try to understand from this example how to find the inverse directly from the unilateral transform. You can see here we are not given any conditions on the region of convergence, okay, but we are given the unilateral transform instead of bilateral, and the unilateral transform implicitly contains information on the ROC. Okay, so what we do first is to, for the denominator, we do a standard decomposition, factorization. So we can find out all the poles of this rational transform. And clearly we have two poles here. One is -2 plus 3j, one is -2 minus 3j. So these are the two roots of the denominator. And you can actually visualize that. So it's -2, one is here, one is here. Right? -2, one is 3j, -3j. And because it's a unilateral Laplace transform, we know that by the fundamental property of unilateral Laplace transform, the region of convergence must be a right-sided plane. Okay? Because by definition, the unilateral transform starts from zeros. So the ROC, we start from 0. So the ROC is always right-sided. And in this example, we have two poles. So the only possibility for the region of convergence is now to the right of these two poles. Okay. So leveraging this property of unilateral transform, we can directly figure out the region of convergence. So in this case, ROC is to the right of -2. And then, okay, now we have the region of convergence. We have the ROC. So the rest is to find out the inverse. We do a partial fraction expansion, very standard step. And then from here, we can figure out the inverse. So for example, here, 0.5 minus 3, this is a constant, numerical constant. So we can keep it. And for the rest of for this fraction number with this ROC, we can figure out the inverse by looking into the table. It's quite standard. And then you can simplify that a little bit. Okay, so here you just need to given this ROC, given this each part of the unilateral Laplace transform, you just need to look into the table, find out the corresponding inverse. And here's an alternative way to solve this problem, which is I will not go into details, but the idea is it's very tricky here. So I mean, the homeworks or in the exams, we will follow the first approach. But here, this is just to note that there's an alternative but more complicated way. So the idea is to rewrite this rational form into such a form. Well, what is special here is that everything is in a complete square. And then why do we need this form? Because in the previous example, we have shown that such a signal, ut times cosine, this signal, the corresponding Laplace transform takes such a form. Well, we have complete squares on the denominator. Then the rest of the step is trying to connect these existing pairs with this Laplace transform. So I think I will skip it here. So apparently this approach is more general and it's actually simpler. And these are the fundamental properties of unilateral Laplace transform. There are some differences between them and the properties of the bilateral transform. First of all, convolution. We know that for the normal Laplace transform, convolution can always transform into multiplication in the S domain under any condition. But here, in order for this to hold for the unilateral transform, we need both signals to be causal. Okay. Yeah, intuitively, this is because we're doing unilateral transform. And then for the differentiation property, this is very important because we want to apply it to analyze differential equations or LTN systems specified by differential equations. So you can see that a differentiated signal is unilateral transform is S times the unilateral transform of the original signal minus the initial condition of the signal. Okay. This is how the initial condition starts to play a role in the unilateral transform. If you do a normal bilateral Laplace transform, we don't have this, right? We just have S times capital XS. But on the unilateral transform, we have this initial condition. And this is the derivation, which I'm going to skip here. But essentially, the idea is that because of this zero negative, it will result in initial condition here. Okay, so this is the first order differentiation property. Now, if we, for the second order, is more different. So you apply this property one more time. For the second order differentiation, the unilateral transform is S squared times XS. This part is the same as the normal Laplace transform. However, we have the other two initial conditions. One is S times the first order initial condition. Now the zeroth order, S times the signal at zero negative, and minus the first order derivative, the initial condition of the first order derivative. Okay. So this one, it involves two types of initial conditions. One is the signal initial condition, one is the derivative signal, the initial condition of the derivative signal. Okay, so let's look at quickly look at one example of how to apply unilateral Laplace transform to solve a differential equation with given initial conditions. So consider this LTI system. Okay. Find the output if the input is given by alpha times ut. So we are given the input signal, and we are given two initial conditions of the output, well, which basically says that at time zero, the output is zero and the derivative of the output is zero. So to leverage these initial conditions, we can just take unilateral transform, right? Because by taking unilateral transform, these properties will naturally involve these initial conditions. So we just take unilateral transform on both sides. And then this second order differentiation, by the property of the unilateral transform, it reduces to this one, okay? So remember, it involves these two initial conditions, but now they are given, okay? So you just need to plug them in. So this one gives such a unilateral transform. And for this first order differentiation, it corresponds to such a unilateral transform. And I think there should be a factor of 3 here. It's missing here. But it doesn't affect the final result because of it's 0. And the last one is basically 2 times ys. Okay, I think there's several things that needs to be updated. These two capital Y should be, it is not the normal Laplace transform. Okay, it's a unilateral transform. So the font style should be the same as this one. Okay, So here we are just taking the unilateral transform and leveraging the differentiation property of the unilateral transform. Okay, so this will naturally introduce these initial conditions. And on the right-hand side, xt is given as alpha times ut. So we know this is a very specific signal. So we can derive the unilateral transform of this signal. Because it is a causal signal, so the unilateral transform is simply the Laplace transform. And the Laplace transform of ut, we know that is given as 1 over s with this ROC. So in the end, the unilateral transform of this one is alpha over s. Okay, now you have this transformation, you plug in all the initial conditions. You have this one. Now you solve this equation. In the end, you get, again, this should be this unilateral transform. Okay, it's not the normal Laplace transform. So the unilateral transform, in the end, you can take such a rational form. And then this one can be, after partial fraction expansion, can be decomposed into 3 fraction numbers. And directly from the unilateral transform, we can directly obtain the signal. Okay. As we discussed in the previous example, given the unilateral transform, the ROC is clear. Because for unilateral transform, the ROC is always to the right of the rightmost pole. So here we have 3 poles. One is 0, -1, and -2. Okay, we have 3 poles. So the ROC is clear from the unilateral transform. It is to the right of the rightmost pole. So here the ROC is this one. So with this ROC, okay, so basically with the unilateral transform, you can figure out the region of convergence by leveraging this property. Now, once you have the region of convergence, the rest of the things that are standard. You look into the table, you can find out the inverse, the signal in the time domain. And this is the signal that we figure out in the time domain. Okay. So this is how, now think about this problem. We are given a system, given a differential equation, given the input, and given the initial boundary conditions. With this, we can apply the unilateral transform and completely solve this equation. So in the end, the output, we can figure out the output. Okay. The output YT takes such a form under this input and under these initial conditions of the system. And here's another example. The only difference is that we modify the initial condition a little bit, but now they are not 0. They may depend on beta and gamma. You follow exactly the same steps, but now these two are not 0. Okay, you plug in beta and gamma, follow the same steps, you can get such a unilateral Laplace transform. Okay. And what happens is that you can divide this into 2 parts. Well, one part is normal, and the other part involves beta and gamma. Well, beta and gamma are the initial conditions. So in the special case, well, beta and gamma are 0, like in the previous example, this part becomes 0. So we only have this part of the unilateral transform. So we call this the 0 state response, which is the response corresponding to a 0 initial condition. And this one is the 0 input response, which corresponds to with initial condition beta and gamma, but with a 0 input. I think these concepts, you must have learned these concepts in the circuit courses. Well, circuit courses. given a circuit, we have 0 state response and 0 input response. And the final output is a superposition of these two. And then this is a general result. So in the end, if you give me a specific input and a specific initial conditions, I can have a specific unilateral transform of the output. And from there, I can figure out the inverse, find out the real output signal. Is the alpha part the homogeneous part of the equation? I'm not sure what does homogeneous is referring to here. But I think alpha specifies the input. Alpha is involved in the input. In here, we are considering a scaled version of the constant input ut. And from here, you can see you can have an understanding of the basic circuit systems, because most of the circuits are described by second-order partial differential equations, and by looking at these equations from a unilateral Laplace transform perspective, you can easily understand this 0 state response and 0 input response. Okay. They are naturally separated by taking the unilateral Laplace transform. Okay, so we're 3 minutes over. So I will stop here. If you have any questions, come to the office hour, and I will send an email confirming the exam schedule, and also I will upload homework 10, the solution to homework 10.
I have a quick question.
Yes.
Is there going to be a practice test for the